Okay, this is lesson 3.2c. So we're talking more about regression, summary statistics here. So this is the formula. So sometimes you know the calculator is pretty much going to calculate if we have the data. Sometimes they don't give us the data; they just give us summary statistics. They give us stuff like the mean of the y values, the mean of the x values, the mean standard deviation of x, the mean standard deviation of y. So if they give you those kinds of things, and maybe the r value, the correlation, we can actually calculate A and B using these two formulas. So there's some formulas that we can use and then write our equation from the formula. So that's definitely possible. One of the reasons why these formulas work, and they have these weird terms, like do you see that y bar and x bar? Those are the average x and average y. One of the reasons that formula works is because that point, if you look at that vertical line there, the x bar there, the mean foot length in this case, and that I think it's blue, that y bar, the mean height, you notice that the regression line, the green line, goes right through the mean x and the mean y. That always happens. That's kind of a thing that happens. Just like the sum of the residuals is 0, the regression line always goes through the mean x and the mean y. Like that point, it's going to go through every time. So that's part of our formula because that's where it always goes through. If you were to draw another line, they drew two more. So they added the standard deviation of y, that's that red line up above, that horizontal line. And to the right of the mean, they put x bar plus the standard deviation of x and drew kind of a greenish line there. And notice that the line doesn't not go through those 2 points, but it goes kind of a little below. They have that question mark, like what is the length of that height? And it's actually has to do with the correlation. If you look back at the formulas, it was r times standard deviation of y divided by standard deviation of x. And so you're actually multiplying that by r to get that distance there. So like in this case, for every increase in one standard deviation in the value of x, the least regression line predicts that an increase of r standard deviations in the response variable y. So it's saying that the rise over run, the rise there is like r, and then the run is s sub x there, so to speak. So it's kind of a thing because, and the values is called regression to the mean. The values regress to the mean. The idea of regressing to the mean is, say two relatively short folks have a child. It's very likely that the child might be taller than both of them because they might both be below the mean, and sometimes heights regress towards the mean. Same type might be true of two tall people who have a child. It's possible that their child regresses towards the mean, their height of the child regresses towards the mean, and since they are both above, it might, the child may be maybe shorter than they are, maybe not as short as the mean, but still above average, but that can happen sometimes. Correlation and regression are powerful tools. Okay, so they only describe linear relationships. You can see some people will try to use R values or correlation to describe curved shapes. That's not that wise here. In this case, you can see this first. That's kind of like your traditional. The top left graph is what you think of. If I said a 0.8, that's moderately strong. You know, the graph looks maybe something like that. But here you have a curved graph. Really looks like it has a strong correlation if you were talking about a curved graph. But as far as linear, it's not that linear at all, but it still has the same 0.816 R value, which is measuring the linear correlation. Bottom left here, that looks really strong, except for that 1 point. That 1 point throws it off from perfect, being 1 for R, all the way to 0.816. And this is just crazy. It's crazy that this one has an R value of 0.816. So you really can't tell much about the form just by knowing the R value. It's just you don't know if it's linear or nonlinear. You just don't know. And so that's something to keep in mind. They're not resistant. There are some points out there with high leverage. Some are called outliers when they have a large residual. Just in general, we can call these points influential points. They're affecting the slope, the y-intercept of the graph, the correlation, coefficient determination. All those things are being affected by any influential point. Again, sometimes those influential points are called high leverage or outliers, or just generally speaking, an influential point. So here you can see child 18. The definition of a high leverage point is one that the much larger or much smaller x values. Well, I see a point on this graph. Child 18 has a much larger x value than all the other points in this data. So child 18 is like 42, age in months at the first word, so he's 42 months old, I guess. But the other ones, so that one child has a huge effect on the regression line, pretty much everything there, just a huge effect. Child 19 has a pretty big effect. So he's called, what do we call that one? We call it an outlier because he has a large residual. Not necessarily, the x value is not unusual, but the residual is very large. And so we call him an outlier. And he has a little bit of effect, maybe especially on the y-intercept there, but it will affect different things that the correlation certainly be affected. Again, we just call those what they are. And so with all 19 points, those are the things. With child 18, so 18 didn't have a huge effect on the standard deviation, but it did, of the residuals, but it did have a big effect on the R-squared value there, coefficient determination. With child 19 included, or without child 19, if you took that one away, that did have a pretty big effect on the standard deviation of the residuals because that was a large residual. So it's going to have a big effect on the standard deviation of the residuals. And R-squared value was also affected quite a bit. So those points have a big influence on things. But they affect things differently depending on where the points are. Okay, again, association does not imply causation. We often, people will say, oh, one causes the other thing to happen. We predict it, but we don't cause it to happen. So let's just play around just for a second here. So this is, one of these where if I draw 2 points, it'll draw the line. That has a perfect correlation because there's only 2 points. If I drew some other points, that's 0.76. I just want to mention something. So I'm going to take that point away. So you can tell this is, definitely positive, moderate correlation here. There's not really strong or weak. It's kind of in the middle. But if I put a point that's kind of on the line but way far away, that would be called a high leverage point, right? So if I put a point over there right on as close as I can to that, the equation for the line won't change. But did you notice the correlation went from moderate to moderately strong? Like it had a huge effect on that. If I were to change this point and move it down, you can see that 1 point now, this whole correlation changed to a negative correlation just with 1 point moving, right? So it can have a huge effect. It can make it very strong or, quite weak, 0 even, you can make it. So you can do lots of changes with those kinds of things, for sure. If you had points like this, looks like a negative correlation, but again, 1 point way up here, that's going to change it quite a bit. And the line, let me do this so the line shows. If I'm over here, wow, it goes from a negative correlation. That point with high leverage is going to move. If I move it vertically, it's going to, oh, that's so weird. So funny to see. It moves that. It's almost changing the y-intercept more than it is the slope when I'm kind of in the middle and just kind of moving up. Just to show you what I was showing you about the x and y lines. Do you see wherever I move this point, do you notice that that blue line goes through the average x and the average y? Those two lines are the average x and average y lines, and no matter where I move this, it's always going to go through the average x, average y line. So it's always going to be true. If you want to play with that, computer app there. You can go to that website and try some different things. It's kind of neat. Okay, random sample of 11 high schools were selected from all high schools in Michigan. That's where I grew up. The percent of students who are eligible for free and reduced lunch and the average SAT math score are sampled and recorded. So we have all that. Student with household income below a certain threshold are eligible for free reduced lunch. Here's a scatter plot with a residual plot. So the left-hand side is the scatter plot, right? We see moderately strong negative correlation here. The R value, it doesn't say what the R value is. Well, it kind of says. So if you didn't catch that, R squared is 85.29. So R squared, so if you go to so we do the square root of 0.8, sorry, let me go back, 0.8529, 0.8529, and that gives you 92. So the R value is 92, but actually it's going to be negative. That's going to be negative that because it's got a negative correlation, so the R value has to be negative. So when you take the square root of that guy to try to figure out what the R value is, because R squared is 0.8529, it doesn't tell you whether it's positive or negative. You have to look at the actual slope here on the line, which is negative, so you know the R value is negative. So the R value would be negative 0.92. So it's pretty strong, but a negative correlation there. We see that to the right here, on the top right, is our what's called the residual plot. I see a lot of scatter there. I don't see a pattern of any kind. So I think a linear fit is definitely a good fit for this model. That's good. Is a line appropriate model? Yes, because the scatter, lack of a pattern found on the residual plot of the top right. Explain how, that's why. Find the correlation. Again, we just did that. I didn't even look at the questions. I was just kind of talking and answered the questions there. You take the square root of that, you get that, but we know it's negative because, again, the slope is negative here. Okay, what's the equation of the least squares regression line? So that's a little tougher there. So we have to look at the computer output. We can tell the slope is negative. That might help you as you figure out which is which. I always look to this word constant. This is from Minitab. So the 577.9 is our constant. That's our y-intercept. The number below it is going to be your slope, negative 1.993. So you would write your equation. I would not write y bar. I would write our y is the average SAT math score. So I would write in parentheses average SAT math score with a little hat above it. That little symbol is hat. So it means the predicted average SAT math score equals 577.9 minus 1.993 times parentheses percent of free reduced lunch. So you want to use actual words there. It's just so much easier than defining the y and the x there. By how much do the actual SAT math scores typically vary from the values predicted by the least squares regression line? That sounds exactly like the standard deviation of the residuals, which is that number 23.3168. The units would be whatever the y-axis, because this is talking about vertical, so whatever the y-axis unit is, which is just test scores, so it doesn't just test scores there, so it's not really a percent or anything there. So again, so 23S is that's standard deviation of the residuals. So the actual SAT math scores typically vary about 23. Again, we're using that definition of standard deviation, typically vary by about that, but we're combining this with the idea of residuals. So from the values predicted by the regression line. So we are talking about residuals there. Good. That's the lesson for today.